Welcome to the mechanics of rest. The universe is defined less by the structures it contains than by the immense expanding intervals that separate them. To look into the deep field of the night is to confront a distance that is not merely a static gap, but an active, accelerating void that is fundamentally redrawing the map of the cosmos with every passing second. If you find these patient explorations of the scientific record valuable, liking the video and subscribing to the channel for our weekly releases is a gentle way to support the work. We are embarking on a journey through the measurements of the intergalactic medium and the unsettling mechanics of cosmic expansion. It is a chronicle of the distances that define our reality, starting with the moment our perspective shifted from a single lonely galaxy to an ocean of island universes. Chapter 1: The Island Universes. The distance from the Earth to the Sun, a measurement of roughly 93 million miles, serves as the fundamental unit for the architecture of our local system. Within this boundary, the orbits of the planets are held in a predictable and familiar stability. The Sun remains the central anchor. Light crosses this interval in 8 minutes. The scale is vast but remains conceptually tethered to the human experience of time and motion. A different order of magnitude defines the structure of the Milky Way. Our home galaxy spans a distance of 100,000 light-years from one edge of its luminous disk to the other. For the greater part of human history, this vast collection of stars was thought to constitute the entire sum of the universe. The hazy patches of light visible in the night sky were classified simply as nebulae. They were believed to be clouds of gas residing within our own borders. The universe was a single, lonely island. The Great Debate of 1920 brought these assumptions into public scrutiny at the Smithsonian Museum of Natural History. Astronomers Harlow Shapley and Heber Curtis presented conflicting evidence regarding the nature of these spiral nebulae. Shapley argued that the Milky Way was so large that everything observed by telescopes must be contained within it. He suggested that the spiral shapes were merely forming star systems. Curtis disagreed with this assessment. He proposed that the spirals were distant, independent systems of stars. The resolution of this disagreement required a measurement that could reach beyond the known limits of the galaxy. Until the early 20th century, the tools for gauging cosmic distance were restricted to the method of parallax, which only functioned for the nearest stars. The spiral nebulae remained blurred and indistinct. Their true nature was hidden by their distance. No one could see individual stars within the swirls. Everything changed when the focus was directed toward the Andromeda Nebula, a prominent spiral in the northern sky. Using the 100-inch Hooker telescope at Mount Wilson, Edwin Hubble spent several nights in 1923 capturing long-exposure photographs of the nebula's outer arms. He was searching for novae, the sudden brightening of dying stars. He found several candidates on his glass plates. He marked them with the letter N. One of these marks was eventually crossed out. The star Hubble identified was not a nova, but a Cepheid variable. This specific class of star pulses with a regularity that is directly linked to its inherent brightness. By measuring the time between the pulses, an astronomer can determine exactly how much light the star is emitting. Hubble compared this known brightness to how faint the star appeared on his photographic plate. The discrepancy revealed the distance. The calculation was undeniable. The result placed the Andromeda Nebula at a distance of nearly 1 million light years, a figure far exceeding the diameter of the Milky Way. This measurement effectively shattered the idea of a single galaxy universe. The nebula was reclassified as a galaxy in its own right. It was a separate island universe. The marks on the plate were definitive. The cosmos had grown larger in a single night. Modern measurements have refined this distance to approximately 2.5 million light years. Between our galaxy and Andromeda, there lies a gap so profound that it contains almost nothing. A few stray stars may drift in this intergalactic medium, but they are rare and isolated. The vacuum dominates the interval. The light we see from Andromeda today began its journey before the emergence of modern humans. It traveled through the void for eons. The discovery of Andromeda's true distance was the first step in mapping the local group. This cluster of galaxies includes the Milky Way, Andromeda, and the Triangulum Galaxy, along with about 50 smaller satellite systems. These bodies are bound together by gravity. They move through the void as a single unit. They are neighbors in a very large neighborhood. Most of the local group is empty space. The ratio of matter to void within this cluster is difficult to visualize. If the Milky Way were the size of a small dinner plate, the Andromeda Galaxy would be another plate located about 20 feet away. In the space between these two plates, there would be nothing but a few microscopic specks of dust. The galaxies are not crowded together. They are isolated by the very medium they inhabit. The void is the primary feature of the landscape. The human mind often struggles to process these intervals without resorting to poetic abstraction. A light year is not a measure of time, but a distance of nearly 6 trillion miles. Multiplying this by 2.5 million produces a number that has no anchor in the physical world of the listener. We rely on the mathematics to hold the weight of the reality. The numbers are the only bridge. The logic remains sound. The chronicler finds a quiet significance in the fact that the most important discovery in cosmology began with a single star in a distant swirl of light. This Sipfeed variable served as a beacon that illuminated the scale of the entire universe. It transformed a cloud of gas into a city of stars. The perspective shifted forever. The isolation was recognized. The stars were grouped into distant families. The transition from a single galaxy model to a multi-galaxy universe required more than just larger telescopes. It required a new way of thinking about the intervals between objects. These intervals are not just empty, they are the most abundant part of the cosmos. Every star seen with the naked eye belongs to our own system. The rest of the universe exists in the gaps between those stars. The dark patches are where the story continues. As the focus of astronomy moved beyond the local group, the distances grew even more difficult to reconcile with previous theories. The methods used to measure Andromeda were only the beginning of a larger effort to gauge the depth of the void. To understand why the distance is worse than it seems, one must look at the tools developed to measure the dark. These tools would eventually reveal a universe that was not just large, but actively moving away from itself. Chapter 2: The Glass Plates of Harvard. The glass photographic plate was the primary instrument for this measurement. a physical record of light captured over hours of exposure. These rectangles of thin, transparent material were coated in a light-sensitive emulsion, designed to hold the faint impressions of distant stars. In the early 20th century, the Harvard College Observatory became a repository for thousands of these plates. They were organized in wooden cabinets, each one representing a specific window into the night sky. The work of interpreting these images fell not to the observers at the telescopes, but to a group of women who meticulously cataloged the brightness of every silver halide grain. Within the quiet rooms of the observatory, the process of measuring the universe was a manual and repetitive labor. The women, known as computers, used magnifying loops to examine the plates. They compared the size and darkness of star images against a calibrated scale. This was a task that required patience and a high degree of precision. It was through this exhaustive scrutiny that the first reliable yardstick for cosmic distance was identified. Henrietta Swan Leavitt was among the most dedicated of these researchers. A graduate of Radcliffe College, she began her work at Harvard in 1895 as a volunteer before becoming a permanent member of the staff. Leavitt was tasked with identifying variable stars, those whose brightness fluctuates over time. She spent years marking the positions of these stars on the glass plates. Her attention was focused primarily on the Small Magellanic Cloud, a hazy satellite galaxy visible from the southern hemisphere. Thousands of stars were documented in her survey. Among them, she discovered a subset that displayed a remarkably consistent pattern of pulsation. These were the Cepheid variables. Unlike other stars that might flicker or flare unpredictably, the Cepheids followed a rhythmic cycle. Their luminosity would rise to a peak and then subside with mathematical regularity. Leavitt recorded the period of these cycles, noting how many days it took for each star to complete its pulse. This specific class of star provided a unique opportunity for measurement because the stars in the Small Magellanic Cloud were all at roughly the same distance from the Earth. Any difference in their apparent brightness had to reflect a difference in their actual, inherent light output. By 1908, Leavitt had cataloged 1,777 variables. She noticed a striking correlation. The stars that were inherently brighter took longer to complete their cycles of pulsation. A fundamental breakthrough arrived in 1912 when Leavitt published a more refined analysis of 25 Cepheids. The data confirmed a linear relationship between the logarithm of the period and the brightness of the star. This became known as the period luminosity relationship. It meant that if an astronomer could measure the time it took for a Cepheid to pulse, they would know exactly how much light that star was producing. The star had become a standard candle. This relationship allowed for a direct calculation of distance across the void. If two candles of identical brightness are placed at different distances, the further candle will appear fainter according to the inverse square law. By knowing the true brightness of a Cepheid from its pulse rate and comparing it to its observed brightness on a glass plate, the distance to that star could be determined with high accuracy. The uncertainty of the intergalactic medium began to yield to the logic of the light curve. Light curves are the visual representations of this data, plotting the rise and fall of intensity over time. For a Cepheid, The curve often shows a rapid brightening followed by a slower decline. The duration of this cycle can range from a single day to over 100 days. Leavitt's work provided the scale that allowed others to calibrate these curves. She turned the stars into reliable markers that could be seen across millions of light years. The logic of the standard candle was soon applied to the broader cosmos. Harlow Shapley used Leavitt's discovery to map the distribution of globular clusters within the Milky Way, determining the size of our own galaxy and our sun's position within it. Later, as the chronicler noted, Edwin Hubble would use the same tool to identify Cepheids in Andromeda. Without Leavitt's meticulous work on the Harvard plates, the distances to other galaxies would have remained a matter of speculation. Astronomers began to see the Cepheids as the essential beacons of the deep field. These stars are massive and highly luminous, often 5 to 10 times the mass of our Sun and thousands of times more brilliant. This luminosity allows them to be detected even when they are located in distant external galaxies. They act as the primary links in the cosmic distance ladder, the series of methods used to gauge the span of the universe. It remains a quiet irony of the scientific record that Leavitt was never fully recognized for this contribution during her lifetime. She was a woman working in a field dominated by men, performing what was then considered clerical labor. Yet, the entire structure of modern cosmology rests upon the period luminosity relationship she identified. Her work provided the first evidence that the universe was far larger than the human mind had previously dared to imagine. The small Magellanic Cloud, where Leavitt found her first variables, is located about 200,000 light-years away. This was a significant distance, but it was still within the local neighborhood of the Milky Way. The real power of the Cepheid variable was its ability to reach further. As telescopes grew more powerful, these pulsing stars were found in increasingly distant systems. Each one confirmed that the gaps between the stars were wider than the stars themselves. At the center of a Cepheid's pulse is a physical mechanism known as the Eddington valve. As the star's atmosphere becomes more opaque, it traps the heat generated by nuclear fusion in its core. This pressure causes the star to expand. As it expands, the atmosphere thins and cools, allowing the heat to escape. Gravity then pulls the outer layers back inward, and the cycle begins again. The pulse is the breath of a giant. Despite the precision of the Cepheid method, it was only the first rung of the ladder. To measure the distances between the most distant galaxies, astronomers needed even brighter markers. The Cepheids are visible across millions of light years, but the universe extends for billions. The tools would have to evolve. The void was deeper than the light of a single pulsing star could reveal. The discovery of the Cepheid relationship established that the universe was measurable. It replaced the vague estimations of the 19th century with a system of quantitative anchors. The glass plates at Harvard were no longer just pictures, they were maps. They revealed that the stars were not randomly scattered, but grouped into structures separated by vast, unlit intervals. These measurements eventually led to the realization that the galaxies were not stationary. While the Cepheids allowed us to see how far away a galaxy was, another instrument was required to see where it was going. The light from these distant systems held another secret. one that would be revealed through the study of the spectrum. The silence of the glass plates was about to be replaced by the data of the moving dark, as the velocity of the galaxies became the next great frontier of the chronicle. Chapter 3: The Velocity of Recession. Milton Humason began his career not as a scientist, but as a mule driver hauling heavy construction equipment up the steep, winding trails of Mount Wilson in the San Gabriel Mountains. After the observatory was completed, he transitioned to a role as a janitor, eventually demonstrating such a keen aptitude for the machinery that he was trained as a night assistant. His journey from manual laborer to a primary operator of the world's most powerful telescope is a quiet testament to the patience required by the scientific record. He became the eyes of the mountain. He learned the rhythm of the stars. He waited for the light. High above the valley floor, the air on Mount Wilson is thin and cold, a condition that provides the clarity necessary for deep sky observation. The atmosphere remains still, allowing the light of distant galaxies to reach the mirror without the blurring effects of lower altitude turbulence. Humason spent hundreds of nights in the unheated dome, perched on a platform high above the floor. He sat in the dark for hours. He guided the telescope. He kept the stars in focus. The 100-inch Hooker telescope was the instrument that made this work possible, a massive assembly of steel and glass that represented the pinnacle of early 20th century engineering. Its mirror, a thick disk of green glass cast in France, had the power to gather light that had been traveling for millions of years. This light was directed into a spectrograph, a device that splits the incoming radiation into its constituent colors. The resulting image is a spectrum. It is a barcode of stellar chemistry. It contains the secret of motion. Spectroscopy provided the means to see beyond the static image on a photographic plate. When the light of a galaxy is passed through a prism, it displays a series of dark absorption lines corresponding to the elements present in the stars, such as hydrogen and calcium. These lines appear at specific known wavelengths. If a galaxy is stationary relative to the Earth, the lines remain in their expected positions. If the galaxy is moving, the lines shift. The shift is the measure of velocity. Vesto Slipher had observed this phenomenon as early as 1912 at the Lowell Observatory in Arizona. He noticed that the spectra of most spiral nebulae were shifted toward the red end of the spectrum, meaning their wavelengths were being stretched. This indicated that these objects were moving away from the Milky Way at high speeds. Slipher's work was the foundation. He identified the motion. He measured the initial redshifts. Working in tandem at Mount Wilson, Edwin Hubble and Milton Humason expanded upon these early observations with the power of the Hooker telescope. While Hubble focused on determining the distances to these galaxies using the Cepheid variables Leavitt had identified, Humason took on the grueling task of capturing their spectra. A single spectrum could require an exposure of several nights. Humason would return to the same faint patch of light night after night. He accumulated the photons. He built the record. The exposures required a level of physical endurance that is rarely associated with modern astronomy. Humason had to manually adjust the telescope's position every few seconds to compensate for the Earth's rotation and atmospheric refraction. He used a guiding eyepiece to keep a single star centered on a pair of crosshairs. The temperature often dropped below freezing. The work was silent. The mountain remained still. A galaxy spectrum is a delicate thing, often no more than a faint smudge on a small strip of film. Humason developed specialized techniques for intensifying these images, allowing him to measure the redshifts of galaxies that were much fainter and more distant than those Slipher had studied. He found that almost every galaxy he observed was receding. The exceptions were only the most local neighbors. The rest were in flight. This phenomenon, known as redshift, is analogous to the Doppler effect heard in sound waves. As a siren moves away from an observer, the sound waves are stretched, resulting in a lower pitch. With light, the stretching of the waves results in a shift toward the longer, redder wavelengths. The faster the galaxy recedes, the greater the shift. Humason's data showed velocities that were staggering. Some galaxies were moving at thousands of kilometers per second. By 1929, Hubble had enough data to combine his distance measurements with Humason's velocities. He plotted them on a simple graph, with distance on the horizontal axis and velocity on the vertical axis. The points fell into a nearly straight line. This indicated a linear relationship between the two values. The further away a galaxy was, the faster it appeared to be moving. The relationship was consistent. The law was born. Hubble's law states that the velocity of recession is proportional to the distance. The constant of proportionality, now called the Hubble constant, represents the rate at which the universe is growing. In the early days, the measurements were rough, suggesting a much higher rate than we recognize today. The current accepted value is approximately 73.3 kilometers per second for every megaparsec of distance. The number is a heartbeat. It defines the tempo of the cosmos. This proportional relationship suggested a profound conclusion about the nature of space itself. If every distant galaxy is moving away from us, and the further they are, the faster they go, it does not mean that the Milky Way is at the center of an explosion. Instead, it suggests that the space between the galaxies is expanding. Every point in the universe is moving away from every other point. The void is growing. The intervals are lengthening. There is a quiet weight to the realization that the universe is not a static container, but a dynamic and changing entity. Before these observations, the prevailing scientific view was that the cosmos was eternal and unchanging. The work at Mount Wilson replaced this stability with a sense of momentum. The galaxies are like markers on a stretching fabric. They stay in place. The fabric grows. One measurement of the galaxy NGC 7619, recorded by Humason in 1929, showed a recession velocity of 3,700 kilometers per second. This was the highest velocity ever recorded at the time. It placed the galaxy at a distance far beyond the local group. It confirmed that the law held true even at the limits of their detection. The pattern was universal. The expansion was real. It was not long before theorists like Georges Lemaitre and Albert Einstein began to reconcile this data with the laws of physics. If the universe is expanding today, it must have been smaller in the past. This led to the conceptualization of a beginning, a moment when all matter and space were concentrated into a single point. The expansion was the result of a process that started eons ago. It continues in the dark. As the velocity of the recession became an established fact, the focus of the chronicle began to shift from the galaxies themselves to the medium they occupied. If the galaxies were moving apart because space was stretching, then the vacuum was not a mere absence of matter. It was a physical participant in the story. To understand the distance between galaxies, one must look at the fabric of the void itself and how it behaves when there is nothing left to hold it back. Chapter 4: The Fabric of the Void. The intergalactic medium exists as the most pervasive and least understood environment in the physical universe. It is the vast, nearly empty corridor that separates one island of stars from the next. While the interior of a galaxy is crowded with stars, nebulae, and planetary systems, the space between is defined by a density so low it challenges the terrestrial definition of a vacuum. This is the domain of the lone atom. In the space between the Milky Way and Andromeda, matter is scattered with extreme sparing. A single cubic meter of this intergalactic volume might contain only one or two atoms of hydrogen or helium. For comparison, the air at sea level on Earth contains approximately 25 quintillion molecules in that same volume. The void is not merely empty, it is a suspension of silence so total that the passage of a single photon becomes the most significant event in a million miles. This material, often referred to as the warm hot intergalactic medium or WIM, consists primarily of ionized gas. It is the residue of the early universe, a thin mist of plasma that never coalesced into stars or planets. It lingers in the dark, heated to temperatures between 100,000 and 10 million degrees by the radiation of distant quasars and the shock waves of galactic collisions. Despite this heat, the gas is so dilute that it would feel cold to any object passing through it. There is simply not enough matter to transfer its energy. Observations made with ultraviolet spectrometers have confirmed the presence of these oxygen and nitrogen ions stretching across the abyss. They form a delicate, invisible web that connects the galaxies, a structure known as the cosmic web. This web acts as a reservoir of baryons, containing nearly half of the normal matter in the universe. It is the scaffolding upon which the visible stars are hung. The distances between galaxies are spanned by these long, thin filaments of gas. Light traveling from a distant galaxy must navigate this medium for millions of years. As it passes through the intergalactic gas, specific wavelengths are absorbed by the stray atoms, leaving a signature known as the Lyman alpha forest in the spectrum. These absorption lines act as markers of the distance the light has traveled. They reveal the density of the clouds it has encountered along the way. The void leaves its mark on the light. Gravity acts as the architect of this vast landscape, pulling matter into dense clusters while leaving behind increasingly empty regions. However, a competing force operates on the background itself. This is the expansion of the cosmos. To understand why the distance is increasing, one must move beyond the idea of galaxies traveling through space and instead consider the behavior of space itself. A length of cooling fabric stretched across a frame begins to lose its tension as it settles. As the fibers are pulled, the weave widens. The gaps between the threads grow larger without the threads themselves changing size. If two small beads were resting on this fabric, they would drift apart not because they were rolling, but because the material beneath them was offering more distance with every passing moment. The cooling of the cloth allows the weave to open further, creating a quiet, persistent expansion. The beads remain fixed to their specific threads, yet the interval between them grows. There is no center to this stretching. Every point on the fabric experiences the same increase in scale. The distance is not something being covered by a traveler, it is something being created by the medium. Under this model, the vacuum is not a passive stage. It is an active, metric property of the universe. Mathematicians such as Alexander Friedmann and Georges Lemaitre were the first to describe this through the Friedmann-Lemaitre-Robertson-Walker metric. This framework suggests that the universe is a manifold where the distance between coordinates is governed by a scale factor that changes over time. Space is not a fixed box, but a flexible sheet. The metric expansion of space explains why the redshift of distant galaxies is proportional to their distance. As light travels through the stretching vacuum, its wavelength is physically pulled along with the fabric of space. A photon that began its journey as blue light is gradually lengthened into red light as the distance it must cover increases. The light is a witness to the growth of the void. It arrives tired and stretched. Distance in this context is a dynamic variable. If the scale factor of the universe doubles, the distance between any two distant galaxies also doubles. This happens regardless of any local motion the galaxies might have. The expansion does not push the galaxies through space, it simply provides more space between them. This process is happening everywhere, at all times, across the entire observable horizon. While the expansion is universal, its effects are not felt within the boundaries of a galaxy. Gravity provides a local counterforce that holds the stars together. The solar system does not expand. The Earth remains at a constant distance from the Sun because the gravitational binding energy is much stronger than the subtle stretching of the vacuum. The expansion only becomes dominant in the regions where gravity has grown weak. These stable, gravitationally bound systems are like small islands of silk sewn onto the larger, stretching fabric. The silk does not stretch, but the gaps between the patches grow wider. The local group remains a coherent unit held together by the mutual attraction of its members. But beyond our immediate neighborhood, the influence of the expansion begins to take hold. The vastness begins to win. Beyond the furthest edges of our local cluster, the scale of the expansion becomes the defining feature of the cosmos. In these regions, the amount of new space being created every second exceeds the ability of gravity to pull things back together. The galaxies begin to recede at speeds that eventually surpass the speed of light, not because they are moving through space that fast, but because the space between us is being added to at such a rate. The scale of this process is difficult to reconcile with the human sense of permanence. We tend to think of the ground beneath us and the sky above us as fixed coordinates. But in the intergalactic deep, there are no fixed coordinates. The map is being redrawn by the vacuum itself. The distances are not just large, They are becoming larger with every breath. As the fabric continues to stretch, the density of the intergalactic medium drops even further. The filaments of the cosmic web are pulled thinner. The lone atoms find themselves further from their neighbors. The universe is becoming a place of increasing isolation, where the light from one island takes longer and longer to reach the next. The void is not just a container for the stars, it is the force that will eventually separate them forever. The realization that space is a dynamic, growing entity led astronomers to look for the limits of this structure. If the universe is a web of filaments and islands, there must be regions where the web is broken. This search revealed the existence of the great voids, vast spherical pockets of nothingness where the expansion has proceeded without any interference from matter. These are the emptiest places in existence, and they represent the next stage in the chronicle of the increasing dark. Chapter 5: The Great Voids and Filaments. 330 million light years across is the diameter of the Bootis void, a region of space so profoundly empty that it challenges the expected distribution of matter in the cosmos. If our own galaxy, the Milky Way, had been situated at the center of this expanse, the existence of other galaxies might not have been confirmed until the development of much more advanced technology. To an observer within that void, the night sky would be almost entirely dark. The nearest neighbors would be so distant that their light would be nearly impossible to detect with early telescopes. This region is a bubble of nothingness in an otherwise articulated universe. This specific measurement defines the largest known hole in the local cosmic structure. It was identified in 1981 during a survey of the northern sky, and it revealed that the universe is not a smooth, uniform mist of stars. Instead, matter is organized into a foam-like architecture. The galaxies are gathered along the edges of vast, empty spheres, forming walls and filaments that stretch across the dark. The voids are the bubbles within this foam, representing the places where gravity has lost the struggle against the expansion of space. Beyond these empty spheres lies the cosmic web, a complex network of gas and dark matter that serves as the blueprint for all visible structures. This web consists of long, thin filaments that act as bridges between dense clusters of galaxies. These bridges are composed of the intergalactic medium described in previous chapters, but here they are concentrated into distinct lanes of travel. Gravity pulls gas and dust along these filaments, feeding the growth of galaxies at the junctions where the threads meet. The universe is a lattice of light draped over a much larger architecture of shadow. Robert Kirshner led the research team that first identified the Buddhist void, using the 1.5-meter telescope at Mount Hopkins to map the redshifts of galaxies in that sector of the sky. The survey was designed to test the large-scale homogeneity of the universe, with the expectation that galaxies would be scattered more or less evenly throughout space. As the data points were plotted, a startling gap appeared in the distribution. Where there should have been thousands of galaxies, there was only a vast, silent interval. The discovery required a total recalibration of how astronomers understood the grouping of matter. The process of recording these distances was a matter of slow, iterative mapping. Kirshner and his colleagues measured the light from hundreds of galaxies, calculating their positions in three-dimensional space. Every measurement confirmed the boundary of the empty region. Since its initial discovery, only a few dozen galaxies have been found within the entire 300 million light year span of the Bootis void. They sit like lonely lanterns in a dark ocean, isolated by distances that dwarf the diameter of the local group. One might observe that the presence of these voids is a direct consequence of the way the early universe began to cool. Shortly after the Big Bang, small fluctuations in the density of matter allowed some regions to have slightly more gravity than others. These dense spots began to pull in surrounding gas, growing larger over millions of years. As the matter moved toward the dense filaments and clusters, it left behind the regions that would become the voids. The emptiness grew as the structures settled. The Great Wall, another immense structure identified in 1989 by Margaret Geller and John Huchra, represents the opposite of the void. It is a sheet of galaxies measuring over 500 million light years in length and 200 million light years in width. This wall is one of many that define the boundaries of the great cosmic bubbles. It sits as a testament to the power of gravity to organize matter over distances that are nearly impossible to comprehend. The galaxies within the wall are close enough to interact, yet they are still separated by the characteristic intervals of the intergalactic medium. Laniakea is the name given to the supercluster that contains the Milky Way and the local group. The term is derived from the Hawaiian language, meaning immense heaven. This supercluster spans 520 million light years and contains the mass of approximately 100 quadrillion suns. It is a watershed of galaxies, where the motion of every star system is governed by a central point of gravitational attraction known as the Great Attractor. All the matter in our local region is slowly drifting toward this invisible center, following the paths laid out by the cosmic filaments. A sense of scale can be found by looking at the Great Attractor itself, a gravitational anomaly located in the direction of the Centaurus and Hydra constellations. It is not a single object, but a massive concentration of matter that pulls on everything within hundreds of millions of light years. Even the expansion of the universe has not yet been strong enough to break the bond between our galaxy and this distant point. We are part of a massive, slow-moving river of stars, caught in a current that flows through the cosmic web. The filaments themselves are not static. They are the conduits for the flow of cold gas into the hearts of galactic clusters. Using sensitive radio telescopes, astronomers have detected the faint signature of hydrogen along these bridges. The gas is the fuel for star formation, moving from the low-density voids toward the high-density nodes of the web. This movement is a patient, eon-long process that ensures the continued evolution of the galaxies. The structure of the universe is a machine for the concentration of matter. Within the Bootis void, the isolation is so extreme that it affects the very evolution of the few galaxies that reside there. Without the frequent interactions and collisions common in dense clusters, these galaxies remain relatively pristine and undisturbed. They do not experience the tidal forces that warp spiral arms or the mergers that create giant ellipticals. They are the hermits of the cosmos, preserved in the stillness of the most empty places. Their light is a rare signal in a vast, unmapped territory. The density of matter in the universe is currently estimated to be about 6 protons per cubic meter. This figure, however, is a global average. In the voids, the density drops to a fraction of this value, while in the filaments and clusters, it rises significantly. The unevenness is the defining characteristic of our era. The universe has spent billions of years becoming less uniform and more structured. The gaps have widened, and the islands have become more distinct. As the chronicle moves further into the deep field, the question arises as to what holds these massive walls and filaments together. The visible matter, the stars, gas, and dust, is not nearly enough to provide the gravitational glue required to maintain such a large-scale architecture. There must be something else, something invisible and pervasive that acts as the scaffold for the cosmic web. This unseen component is the reason the galaxies do not simply drift away into the expanding dark. To understand the permanence of these structures across such vast distances, the focus must shift to the invisible scaffold that dictates the shape of the void. This scaffold is the hidden mass that governs the rotation of galaxies and the movement of clusters. It is the dark foundation upon which the light of the universe is built, and its discovery would eventually reveal that the visible world is only a small fraction of the total reality. This hidden influence is the next subject of the chronicle. Chapter 6: The Invisible Scaffold. 1933 was the year when the first cracks appeared in the accounting of the visible universe. Fritz Zwicky, a Swiss-born astrophysicist at the California Institute of Technology, directed his attention toward the Coma cluster. This massive grouping of over 1,000 galaxies is located hundreds of millions of light-years away. He was attempting to calculate the total mass of the cluster by measuring the velocities of the individual galaxies within it. The motion of the galaxies was a result of the gravity holding the group together. He expected the speeds to be relatively low. The results of the survey were physically impossible according to the laws of Newtonian gravity. Zwicky found that the galaxies were moving much faster than the visible mass of the stars and gas could explain. For the galaxies to remain bound to the cluster at those speeds, there had to be at least 400 times more mass than what was being detected by the telescopes. If the visible matter were the only source of gravity, the cluster would have flown apart eons ago. The galaxies were moving too quickly to be held. Zwicky coined the term Dunkel materia, or dark matter, to describe this missing component of the cosmic record. He suggested that some form of invisible material was providing the additional gravitational pull required to keep the clusters intact. This proposal was largely ignored by the scientific community for decades. It was considered a mathematical curiosity rather than a physical reality. The silence surrounding the discovery lasted for nearly 40 years. The vacuum was assumed to be empty. The evidence became undeniable in the late 1960s through the work of Vera Rubin and Kent Ford. Rubin was a patient observer who sought to understand the rotation of individual spiral galaxies. She used a sensitive new spectrograph to measure the velocity of gas and stars at various distances from the galactic center. She sat in the control rooms of the Kitt Peak National Observatory, carefully recording the Doppler shifts. The data was clear and consistent. It did not match the predictions. In a standard system like the solar system, the planets furthest from the center move more slowly because the gravitational pull of the sun weakens with distance. Mercury travels much faster than Neptune. Rubin expected to see a similar drop off in velocity at the edges of spiral galaxies. Instead, she found that the stars at the far reaches were moving just as fast as those near the center. The rotation curve did not fall, it remained flat. This flat rotation curve meant that the galaxies were embedded within a much larger, invisible structure. There was mass where there appeared to be only empty space. This unseen halo provided the gravity that allowed the outer stars to maintain their high velocities without being flung into the intergalactic void. Rubin's observations were repeated across dozens of galaxies. The results were the same in every instance. The invisible scaffold was everywhere. Current models suggest that this dark matter halo extends far beyond the visible disk of a galaxy, often reaching 5 to 10 times further into the dark. While a galaxy like the Milky Way might be 100,000 light years across, its dark matter influence spans over 1 million light years. This halo acts as a buffer between the galaxy and the intergalactic medium. It is the first line of defense against the expansion of space. The structure is anchored in the shadow. There is a quiet humility in the realization that everything we have ever seen, every star, planet, and nebula, is merely a dusting of snow on a much larger mountain of invisible matter. The baryonic matter, the atoms that make up the human body and the sun, accounts for only 5% of the total mass energy of the universe. Dark matter accounts for roughly 27%. We are the minority in our own home. The universe is mostly dark. Gravitational lensing provides another method for mapping this invisible scaffold across the vast distances between galaxies. When light from a very distant galaxy passes near a massive cluster of dark matter, the gravity of the dark matter bends the light, creating distorted or multiple images. This effect, predicted by Einstein's general relativity, allows astronomers to see the shape of the dark matter distribution. They can map the mass without seeing the light. The gravity leaves a signature. The bullet cluster, a system where two clusters of galaxies have collided, provided a definitive look at dark matter in 2006. During the collision, the visible gas clouds slowed down as they interacted with each other. The dark matter, however, passed right through the collision without stopping. The center of the mass and the center of the visible light became separated. This confirmed that dark matter is a distinct physical substance. It does not interact with light or itself. Within the cosmic web, dark matter serves as the primary driver of structure. It was the dark matter that first began to clump together in the early universe, creating the gravitational wells into which the hydrogen gas eventually fell. The filaments of the web are essentially conduits of dark matter. The galaxies are simply the luminous highlights where the dark matter density is highest. The web is a dark construction. The stars are the decoration. The nature of the dark matter particle remains a subject of intense research and debate. Theoretical physicists have proposed several candidates, including weakly interacting massive particles, or WIMPs, and extremely light particles called axions. These particles are thought to pass through the Earth and the human body by the billions every second without leaving a trace. Detectors located deep underground in former gold mines wait for a single collision. The search is a quiet one. The signal is rare. The discovery of the invisible scaffold fundamentally changed the chronicle of intergalactic distance. Without the binding energy of dark matter, the large-scale structures of the universe could not exist. The expansion of the universe would have shredded the early gas clouds before they could form stars. Dark matter provided the necessary resistance. It acted as a gravitational tether. It held the universe together while the vacuum tried to push it apart. The scaffold was the anchor. As the distance between galaxies is measured, the role of dark matter becomes a factor in every calculation. It defines the mass of the clusters and the rate at which they can attract new members. However, even this massive invisible influence has a limit. While dark matter can hold a cluster together, it cannot stop the expansion of the space between the clusters. The scaffold is strong, but the vacuum is persistent. The balance is shifting. The study of these vast intervals eventually led to a realization that was even more unsettling than the presence of invisible matter. While dark matter provides an inward pull, there is another component of the universe that provides an outward pressure. This component does not reside in the matter, but in the vacuum itself. To understand why the distance is worse than we thought, the chronicle must look at the pressure of nothing. This is the weight of the empty space. Chapter 7: The Pressure of Nothing. The equations of general relativity, finalized in 1915, carried a consequence that their creator found difficult to accept. These mathematical descriptions of gravity and spacetime suggested that the universe was inherently unstable, a structure that must either be expanding or contracting under its own weight. For Albert Einstein, this was an aesthetic and philosophical problem. He, like most of his contemporaries, operated under the assumption that the cosmos was a static and eternal arrangement of matter. The idea that the universe could change its size seemed to contradict the fundamental permanence of the heavens. This preference for stability led to a tactical modification of the mathematical record. In 1917, Einstein introduced a new term into his field equations, a Greek letter known as lambda, or the cosmological constant. This term represented a property of the vacuum that provided an outward pressure, a repulsive force that perfectly balanced the inward pull of gravity. It was a mathematical placeholder, a weight placed on one side of a scale to prevent it from tipping. By adding this constant, Einstein created a universe that could stand still, frozen in a state of perpetual equilibrium. A profound pressure exists in the absence of light, a quality of stillness that is not the same as a lack of activity. In the deepest reaches of a sunless ocean, the weight of the water is felt not as a movement, but as a persistent, encompassing presence. It is a state of equilibrium where every direction is identical, and the cold is a structural property of the environment. The water does not need to flow to exert its influence. Its mere existence defines the conditions of the space. It is a stillness that is heavy with the potential of the mass above it. Light does not penetrate these depths, yet the volume is not empty. It is saturated with a quiet potential. The silence is a dense medium that holds everything within it in a state of suspended animation. There is no wind, no current, only the vast, unwavering pressure of the mass itself. In this environment, the concept of a vacuum begins to take on a physical weight, a sense that the nothingness is itself a substance that can be measured and felt by the structures that inhabit it. The stillness is the dominant force, a persistent background that remains unchanged regardless of what passes through it. The introduction of the cosmological constant was initially seen as a triumph of theoretical elegance, but the data from the mountains of California would soon render it obsolete. As the chronicler noted, the observations of Edwin Hubble and Milton Humason demonstrated that the galaxies were already in motion. The universe was expanding. The static model was no longer supported by the evidence. Einstein traveled to Mount Wilson to see the redshifts for himself, looking through the same eyepiece that Humason had used to map the receding galaxies. He saw the shift in the spectrum, and he realized that the balance he had invented was unnecessary. When the data confirmed the expansion, Einstein famously removed the cosmological constant from his equations. He reportedly described the insertion of the term as his greatest blunder. He believed that if he had trusted the original mathematics of his theory, he might have predicted the expansion of the universe before the telescopes had seen it. The constant was discarded, and for several decades it was treated as a relic of a discarded era of physics. The universe was assumed to be expanding simply because of its initial momentum, and the vacuum was once again thought to be a passive, empty stage. This retraction, however, was not the end of the story for the energy of nothing. Modern quantum field theory suggests that the vacuum is not truly empty, but is instead teeming with virtual particles that appear and disappear in fractions of a second. This quantum foam implies that space itself has an inherent energy density. While the calculations of this energy at the subatomic scale yield a number that is far too large to reconcile with the observable universe, the principle remains. The vacuum possesses a physical weight. Nothingness has a pressure. Modern physics eventually brought the cosmological constant back into the fold, though for a different purpose than Einstein had intended. Instead of keeping the universe static, this energy is now understood to be the driver of the expansion itself. It is a property of space that does not dilute as space expands. If you have a cubic meter of vacuum, it has a specific amount of energy. If that volume expands to 2 cubic meters, you have twice as much energy. The energy is a fundamental characteristic of the interval. There is a quiet paradox in the fact that the emptier the universe becomes, the more energy it contains. As the distance between galaxies increases, more vacuum is created. This new vacuum exerts its own outward pressure, which leads to further expansion, which in turn creates more vacuum. It is a self-reinforcing process that operates on the largest possible scales. The pressure of nothing is the engine of the cosmic widening. Every cubic meter of space contains a tiny amount of this energy, roughly equivalent to the mass of a few hydrogen atoms. At the scale of a laboratory or even the solar system, this effect is completely undetectable. The gravity of the Earth and the Sun is far too strong to be influenced by the subtle push of the vacuum. But across the millions of light years that separate the galaxies, the effect accumulates. In the vast unlit corridors of the intergalactic medium, the pressure of nothing becomes the dominant force in the history of the cosmos. While gravity is a force that pulls matter together, the cosmological constant is a force that pushes space apart. For the first several billion years after the Big Bang, the density of matter was high enough that gravity was the primary architect of the universe. It gathered the gas into filaments and the stars into galaxies. But as the expansion continued and the matter was spread thinner, the density of the vacuum energy began to catch up. About 5 billion years ago, the balance shifted. The outward pressure began to exceed the inward pull. This outward pressure is what prevents the universe from eventually collapsing back in on itself. If the expansion were driven only by the initial momentum of the Big Bang, gravity would eventually slow it down, leading to a big crunch. But the energy of the vacuum acts as a persistent accelerator. It ensures that the expansion will not only continue, but will move into a new, more aggressive phase. The vacuum is not a brake, it is a gas pedal that is permanently held down. The stability of the void is the baseline of the universe. While the stars burn through their fuel and the galaxies collide and merge, the energy of the space between them remains constant. It is the most stable property of the physical world. It does not decay, it does not age, and it does not change its temperature. It simply persists, providing a steady, unyielding pressure that redrafts the map of the cosmos one light year at a time. As the chronicle considers the weight of this invisible pressure, it becomes clear that the distance between galaxies is not a fixed measurement. It is a dynamic and evolving quantity. The work of the early pioneers, Leavitt, Hubble, and Humason, revealed that the universe was larger and more mobile than expected. But the discovery of the vacuum's own energy revealed that the situation was even more profound. The expansion was not merely a movement, it was a quickening. The realization that the expansion of the universe was speeding up arrived in the late 20th century as astronomers looked further into the past than ever before. They used the light of dying stars to measure the rate of expansion at different eras of history. What they found was a universe that was moving away from itself at an ever-increasing pace. To understand the full scale of this acceleration, the chronicle must move from the theoretical pressure of the vacuum to the direct observations of the deep field. This is the story of the accelerating dark, where the distance is not just large, but actively becoming unreachable. Chapter 8: The Accelerating Dark. A sudden flare in a distant galaxy, lasting only a few weeks before fading back into the dark, provides the most precise measure of the deep cosmic field. This phenomenon is the Type 1a supernova, a thermonuclear explosion of a white dwarf star. These events occur with a remarkable uniformity because they are governed by a specific physical limit. When a white dwarf, the dense remnant of a star like our Sun, accumulates enough matter from a companion star to reach exactly 1.4 times the mass of the Sun, it can no longer support its own weight. The resulting collapse triggers a runaway fusion reaction that consumes the star in seconds. Because every such star explodes at the same mass, every explosion produces the same amount of light. This uniformity makes the Type 1a supernova a superior standard candle for measuring the furthest reaches of the universe. While Cepheid variables allow astronomers to reach out millions of light years, these supernovae are so bright they can be seen across billions. They are the lighthouses of the deep past. By measuring how faint these explosions appear, researchers can calculate the distance to the host galaxy with a high degree of confidence. In the late 1990s, two independent teams of astronomers set out to use these flares to answer a fundamental question about the fate of the cosmos. The Supernova Cosmology Project and the High Z Supernova Search Team were engaged in a quiet race to measure the deceleration of the universe. At the time, the prevailing scientific consensus was that the expansion initiated by the Big Bang would eventually be slowed down by the collective gravitational pull of all the matter in the universe. It was assumed that the expansion was like a ball thrown into the air. Eventually, the upward momentum would fade and gravity would take over. The only question was whether the universe would stop expanding entirely or simply slow to a crawl. Adam Rees, Saul Perlmutter, and Brian Schmidt led these efforts, utilizing digital sensors on some of the world's largest telescopes to hunt for the telltale smudge of a supernova. The process involved taking images of the same patch of sky weeks apart and using software to subtract the first image from the second. Anything that remained was a new source of light. This was a labor of data-heavy scrutiny, requiring the coordination of observatories across the globe and the precise calibration of light curves. The astronomers were looking for a subtle brightening in galaxies that had been traveling for half the age of the universe. As the data from the 1998 season began to settle, a discrepancy emerged that troubled the researchers. The distant supernovae were not where they were expected to be. Specifically, they were roughly 10 to 15% fainter than they should have been in a universe where expansion was slowing down. For an object to appear that faint, it had to be further away than the standard models predicted. The only logical conclusion was that the expansion of the universe had not been slowing down at all. It had been speeding up. There was a quiet moment of professional hesitation as the teams checked and rechecked their calculations. Adam Rees recorded the realization in his notes, noting that the omega value appeared to be negative in his initial equations, a result that seemed physically impossible. It suggested that there was a repulsive force at work that was stronger than gravity. The teams eventually realized they were seeing the influence of the cosmological constant that Einstein had discarded decades earlier. The vacuum was winning the tug of war. The term dark energy was coined by cosmologist Michael Turner to describe this mysterious influence. It is not dark in the sense that it is made of dark matter. It is dark because it is entirely transparent and currently beyond the reach of direct detection. It is a property of the vacuum itself, a persistent energy density that pushes outward on the fabric of space. As the universe expands and creates more space, the total amount of dark energy increases, further accelerating the expansion. The more the universe grows, the faster it grows. This discovery redrew the timeline of the cosmos. For the first 7 billion years of its history, the universe was dense enough that gravity was the dominant force, slowing the initial expansion. This was the era of structure formation, when the great walls and filaments of the cosmic web were established. But as the galaxies drifted further apart and the matter density dropped, the outward pressure of dark energy took over. About 5 or 6 billion years ago, the universe reached an inflection point. It began to accelerate into the dark. A transition occurs when a system moves from a state of momentum to a state of active propulsion. If one considers a vehicle coasting up a long, gentle incline, the expectation is a gradual loss of speed as the summit is approached. But if an engine suddenly engages and begins to push, the motion changes from a fading drift to a steady, increasing climb. The summit is never reached. Instead, the vehicle moves away with a quiet, persistent force that grows more powerful as more distance is covered. The coasting phase is a memory. The propulsion is the new reality. This acceleration has profound implications for the future of the intergalactic medium. Because the space between galaxy clusters is stretching at an increasing rate, these clusters will eventually be moving away from us faster than the speed of light. This does not violate the laws of physics, as it is the space itself that is expanding, not the galaxies moving through it. One by one, distant galaxies will cross the cosmic event horizon. Their light will no longer be able to reach us. They will vanish from the observable sky forever. The universe is currently estimated to be about 70% dark energy. This means that the vast majority of the stuff in existence is this invisible, repulsive pressure. It is the dominant player in the long-term history of the cosmos. The distance between galaxies is worse than we thought because it is not just a gap we have to cross. It is a gap that is actively trying to separate us from everything else in the universe. We are living in a brief window of time when the rest of the cosmos is still visible. Interpretive asides in the scientific record often point to the year 1998 as the moment cosmology moved from a study of the past to a study of a disappearing future. The Nobel Prize in Physics was awarded to Rees, Schmidt, and Perlmutter in 2011 for this work, acknowledging the fundamental shift in our understanding. The universe is not a stable home, nor is it a simple explosion. It is a structure that is fundamentally self-dissolving. The accelerating dark ensures that the voids between the filaments will continue to grow larger and emptier. The Buddha's void and its siblings are the precursors of what the entire universe will eventually become. As dark energy continues to push, the cosmic web will be stretched until the filaments snap. The clusters will become isolated islands in an infinite unlit ocean of vacuum. The distance will eventually become an absolute barrier. While the supernovae provided the evidence for the current acceleration, they could not reveal the state of the universe at its very beginning. To understand the origin of the distances we see today, astronomers had to look for a different kind of light. This was a light that had been traveling since shortly after the Big Bang, a faint echo of the first moments of the cosmos. By studying this ancient radiation, they could see the seeds of the expansion before the stars even existed. This relic of the first light is the next chapter in the Chronicle of the Void. Chapter 9: The Echo of the First Light. The Holmdel-Horn antenna, a 20-foot tall aluminum structure shaped like a massive sugar scoop, stands as a quiet monument to the accidental nature of some of the most profound discoveries in the scientific record. It was constructed in 1959 by Bell Telephone Laboratories in New Jersey to support the ECHO satellite project. This was an early experiment in global communications that utilized reflective balloons in orbit. To function as a radio telescope, the antenna had to be exceptionally sensitive, capable of detecting the faintest whispers of electromagnetic radiation while excluding the cacophony of terrestrial noise. It was a precision instrument designed for a world of quiet signals. Arno Penzias and Robert Wilson, two radio astronomers at Bell Labs, inherited the antenna in 1964 for the purpose of mapping the radio emissions from the outskirts of the Milky Way. Before they could begin their survey, they had to establish a baseline of absolute silence. They turned the horn toward empty patches of sky, expecting to find a reading of 0. Instead, they encountered a persistent low-frequency hiss that they could not explain. It was a steady hum at a wavelength of 7.35 centimeters, a noise that did not change regardless of which way the antenna was pointed. The search for the source of this interference became an exercise in meticulous technical troubleshooting. Penzias and Wilson considered every possible terrestrial culprit, from the radar of nearby airports to the broadcast towers of New York City. They checked the internal circuitry for loose connections and cooled the receiver with liquid helium to minimize thermal noise. When the hiss remained, they turned their attention to the physical interior of the horn itself. They found that a pair of pigeons had taken up residence in the throat of the antenna, coating the aluminum surface in what Penzias later described as a white dielectric material. In a patient attempt to reclaim their instrument, the two astronomers spent a day in 1965 scrubbing the interior of the horn, removing the pigeons and their residue. They worked by hand, ensuring that every square inch of the metal was as clean as the day it was manufactured. They believed they had finally eliminated the last possible source of noise. But when they reactivated the receiver, the 7.35 centimeter hiss returned with the same unwavering intensity. It was not the pigeons, and it was not the equipment. The noise was coming from the sky itself. A few miles away at Princeton University, a group of theorists led by Robert Dicke and Jim Peebles had already predicted the existence of such a signal. They were working on the idea that if the universe had begun in a hot, dense state, a relic of that initial heat should still be visible today. They calculated that after billions of years of expansion, the intense radiation of the early cosmos would have been stretched into the microwave spectrum. As Penzias and Wilson struggled to clean their antenna, Dicke reportedly told his colleagues that they had been scooped. The persistent hiss was the cosmic microwave background, the oldest light in the universe. The nature of this light provides a direct look at the universe as it existed roughly 380,000 years after the Big Bang. Before this moment, the cosmos was a hot, opaque plasma of free electrons and protons that scattered photons like a thick fog. As the universe expanded and cooled, the electrons and protons combined to form neutral hydrogen atoms, a process known as recombination. The fog cleared, and the first light was finally free to travel through space. This light has been traveling for nearly 14 billion years, carrying the imprint of the infant universe across the void. Wavelength stretching is the reason this ancient light is no longer visible to the naked eye. When it was first released, the radiation was as bright and hot as the surface of a star. But as the space through which it traveled expanded, the photons were physically pulled apart, their wavelengths lengthening from the visible spectrum into the microwave range. This process is a more extreme version of the redshift observed by Humason and Hubble. The light has been stretched by a factor of over 1,000. It arrived at the Holmdel Horn as a cold, faint echo, representing a temperature of only 2.7 Kelvin. The cosmic microwave background is remarkably uniform, appearing almost identical in every direction. This uniformity suggests that the early universe was exceptionally smooth, with matter distributed with high precision. However, when the signal was mapped with greater detail by the Cosmic Background Explorer, or COBE, in 1989, tiny variations were discovered. These fluctuations, representing temperature differences of only 1 part in 100,000, were the seeds of the large-scale structure we see today. The dense spots in the microwave background were the birthplaces of the first filaments and voids. George Smoot and John Mather, the lead scientists for the COBE mission, provided the first definitive proof of the black-body curve of the microwave background. Their data followed the theoretical predictions with such accuracy that it is often cited as the most perfect measurement in the history of science. The universe, in its earliest stages, was a perfect thermal radiator. The distances between the stars were once so small that heat could be shared evenly across the entire horizon. The expansion of the void began from a state of total connection. Following the success of COBE, the Wilkinson Microwave Anisotropy Probe and the Planck satellite provided even higher resolution maps of these ancient fluctuations. These missions allowed cosmologists to determine the age, composition, and expansion rate of the universe with unprecedented precision. They confirmed that the universe is 13.8 billion years old and that its geometry is remarkably flat. The measurements revealed that the large-scale structure of the cosmic web is not a random occurrence, but a direct consequence of the quantum ripples present at the moment of recombination. An interpretive aside in the Chronicle observes that the noise Penzias and Wilson tried so hard to eliminate was actually the most important signal they would ever detect. They were awarded the Nobel Prize in Physics in 1978 for their discovery, a reminder that the universe often reveals its deepest secrets when we are looking for something else. The hiss of the microwave background is a persistent background radiation that fills every cubic centimeter of space. Even when we look at the emptiest parts of the Buddha's void, we are looking at a space that is saturated with the light of the first moments. The distance this light has traveled defines the boundary of the observable universe. This boundary, known as the particle horizon, is the limit of how far we can see. Because the speed of light is finite, we can only see objects whose light has had enough time to reach us since the beginning of the cosmos. As the universe continues to expand, this horizon moves further away, but it also contains a paradox. Because space is expanding faster than light can travel, some of the light that is currently beyond the horizon will never reach us. The universe is growing larger than our ability to observe it. The scale of this horizon is currently estimated to be about 46 billion light-years in every direction. This figure, often called the comoving distance, accounts for the fact that the galaxies that emitted the light we see today have continued to move away from us during the billions of years the light was in transit. We are at the center of a sphere of visibility that is constantly being encroached upon by the accelerating dark. The voids we see in the microwave background were the origins of the intervals that now separate the galaxies. As the chronicle reflects on this ancient radiation, it becomes clear that the distance between galaxies is worse than it seems because the source of the distance is so deeply embedded in the history of space. The intervals began as tiny fluctuations and have been stretched into the immense gulfs of the modern era. We are living in a time when the light from the past can still reach us, but the window is slowly closing. This horizon marks the boundary of what can be known, leading the chronicle toward the final limits of the observable world. Chapter 10: The Horizon of Visibility. 93 billion light years is the current estimated diameter of the sphere we call the observable universe. This distance represents the absolute limit of what can be perceived from our position in space, a boundary defined by the age of the cosmos and the finite speed of light. Within this volume, there are approximately 2 trillion galaxies, each containing hundreds of billions of stars. Light has been traveling from the furthest of these systems since the era of recombination, crossing the widening void to reach our detectors. The scale is a direct result of the 14 billion year history of cosmic expansion. At the center of this sphere sits the observer, though this does not imply a privileged position in the landscape. Every point in the universe is the center of its own observable bubble, a horizon of visibility that extends equally in all directions. Because light takes time to travel, looking further into the distance is synonymous with looking further back into time. We see the moon as it was a second ago, and the furthest galaxies as they were when the universe was only a fraction of its current age. The horizon is a wall of time as much as it is a wall of space. Because light is the carrier of all information, the particle horizon represents the limit of our causal connection to the rest of reality. Anything beyond this boundary is currently unreachable and unknowable. The photons from those distant regions have not had enough time to span the interval since the beginning of the cosmos. As the universe ages, the horizon naturally expands, allowing light from more distant structures to finally reach us. Every day, the observable universe technically grows slightly larger as new light arrives from the dark. Commoving distance is the term astronomers use to describe the actual physical gap between us and a distant object today. While the light from a galaxy might have traveled for 13 billion years, that galaxy is not 13 billion light years away. During the time the light was in transit, the space between the galaxies continued to stretch due to the expansion of the vacuum. The galaxy that emitted the light we see today is now located approximately 46 billion light years from our own. The map of the universe is being drawn on a surface that refuses to remain still. A thick gray vapor clings to the surface of a landscape, obscuring the distant ridges and valleys from view. As time passes, the particles of the mist begin to drift further apart, not through a sudden wind, but through a patient, internal thinning of the air itself. The density of the atmosphere drops steadily. Objects that were once entirely hidden begin to suggest their shapes through the haze, appearing first as faint shadows before their details are slowly revealed. The world seems to grow as the obstruction recedes into the background. The thinning continues until the air achieves a state of total transparency, yet the furthest reaches remain lost to the eye. The distance is not obscured by the mist, but by the sheer absence of any signal returning from the far horizon. The landscape does not end, but the ability to perceive its depth reaches a physical limit. The light simply does not have enough time to bridge the gap. The observer stands in a circle of clarity that is surrounded by a vast silent territory that remains permanently out of reach. The stillness of this limit is a structural property of the environment. There is no line in the sky, no physical barrier that marks the end of the observable. There is only the gradual fading of signals as they approach the boundary of time. The vacuum remains the same on either side of the horizon, carrying the same potential and the same energy. The only difference is the connection. On one side, the universe is a part of the record. On the other, it is a mystery that is yet to arrive. This thinning of the perceptible world is the mechanism by which the universe maintains its isolation. The expansion of the vacuum acts as a filter, allowing only a certain amount of light to survive the journey across the deep field. As the rate of expansion increases due to dark energy, the filter becomes more restrictive. The distances are growing faster than the light can cover them. This leads to a phenomenon where galaxies that are currently visible will eventually cross the horizon and disappear from view. Galaxies located at the very edge of our visibility are currently receding from us at speeds that exceed the speed of light. This is possible because it is the space itself that is stretching, a process that is not limited by the universal speed of information. The light they emit today will never reach the Milky Way. It is being launched into a headwind of expansion that is simply too strong to overcome. We are seeing these galaxies as they were in the ancient past, but we are looking at ghosts. Their present state is already lost to us. The Hubble sphere is the specific radius at which the expansion velocity exactly equals the speed of light. Objects beyond this sphere are moving away so fast that their photons are effectively walking up a descending escalator. To an observer, these distant systems appear to slow down and redden as they approach the limit. Their light is stretched until its wavelength becomes infinite. They do not wink out of existence. They simply fade into a silence that the telescopes can no longer interpret. A quiet observation in the chronicle notes that we are living in a unique epoch of cosmic history. In the very early universe, the horizon was small and the galaxies were close together. In the very far future, the expansion will have pushed everything so far apart that the observable universe will contain only our own local cluster. We exist in a window of time where the large-scale structure of the cosmic web is still visible. We can still see the walls and the voids. The evidence of the Big Bang is still written in the sky. The total universe, the entirety of space beyond our horizon, is theorized to be significantly larger than the part we can see. Some models, based on the theory of cosmic inflation, suggest that the total universe is at least $10.23 times larger than the observable sphere. If this is true, the part we see is like a single grain of sand on a vast, endless beach. The physical laws are assumed to be the same in those distant regions, but they are forever separated from our history. The isolation is absolute. The cosmological principle states that on a large enough scale, the universe is both homogeneous and isotropic. This means that no matter where you are, the universe looks more or less the same in every direction. If you were to travel to a galaxy at the edge of our horizon, you would see a new observable sphere centered on your new location. You would see new galaxies that are invisible to us, and you would see the Milky Way sitting at the edge of your own horizon. The void is a repetitive and consistent landscape. As the chronicle reflects on these boundaries, the precision of our measurements becomes the focus of the investigation. The fact that we can see to the edge of the observable universe is a testament to the tools we have developed. However, these tools have recently revealed a discrepancy in our understanding of the expansion rate itself. The measurements of the early universe do not perfectly match the measurements of the modern era. This conflict suggests that there may be a flaw in the map or a missing piece of physics. This tension in the data is the current frontier of cosmology. It involves the very anchors of distance that the chronicle has traced, the Cepheids, the supernovae, and the microwave background. To understand why the expansion of the universe is even more complex than it appears, one must look at the disagreement between the light of the beginning and the light of today. This is the Hubble tension, the quiet crisis that defines the modern search for the true scale of the void. Chapter 11: The Hubble Tension. It is not common for a discipline defined by extreme precision to encounter a disagreement that refuses to resolve itself through the accumulation of better data. In the study of the cosmos, most discrepancies eventually dissolve as instruments become more sensitive and techniques more refined. The history of science is largely a record of narrowing margins and settling debates. However, the current understanding of the expansion of the universe is shadowed by a persistent and widening gap between two different methods of measurement. This conflict, known as the Hubble tension, suggests that the distance between galaxies is governed by a logic that remains partially hidden from our view. This specific conflict centers on the value of the Hubble constant, the number that dictates the rate at which the vacuum is stretching. For decades, the goal of cosmology was to determine this number with a precision of 10%. As the Chronicle has traced, the work of the early 20th century provided the first rough estimates, which were later sharpened by the Hubble Space Telescope and the discovery of dark energy. By the early 21st century, astronomers believed they were on the verge of a definitive answer. They expected the different ways of measuring the expansion to converge on a single, harmonious value. Measurements of the early universe provide the first set of coordinates for this calculation. The Planck satellite, a mission launched by the European Space Agency, spent 4 years mapping the cosmic microwave background with unprecedented detail. By analyzing the tiny temperature fluctuations in this ancient light, scientists could use the standard model of cosmology to predict how fast the universe should be expanding today. The logic is based on the physics of the beginning, the density of matter, the pressure of radiation, and the initial rate of expansion. It is a calculation of the present based on the DNA of the past. The Planck satellite results were remarkably precise, yielding a Hubble constant of 67.4 kilometers per second for every megaparsec of distance. This measurement carries an uncertainty of less than 1%, representing the gold standard of early universe physics. It describes a universe that is expanding at a steady, predictable pace, dictated by the cold radiation of the Big Bang. If our understanding of the cosmos were complete, every other method of measurement should arrive at this same number. The light from the beginning should agree with the light of the modern era. Conversely, the measurements of the local universe tell a different story. These observations do not rely on models of the early cosmos, but on the direct measurement of distances to nearby galaxies using the cosmic distance ladder. This is the method perfected by the SHCO's project, an acronym for supernovae, H0's temper zeros, for the equation of state of dark energy. This team uses the Hubble Space Telescope to observe Cepheid variables and Type 1a supernovae in galaxies that are relatively close to our own. They measure the distance and the redshift directly, without the need for theoretical assumptions about the infant universe. Adam Rees, the Nobel laureate who co-discovered the accelerating expansion, led the SHCO's effort to reach a precision of 1%. The project involved hundreds of orbits of the Hubble telescope, carefully recording the pulses of thousands of Cepheid stars. The team accounted for every possible source of error, from the dust in the intergalactic medium to the chemical composition of the stars. When the data was finalized, the result was consistently higher than the Planck measurement. The local universe appeared to be expanding at a rate of 73.2 kilometers per second per megaparsec. Between these two values lies a discrepancy of about 9%. In many fields of study, a 9% difference might be considered a rounding error, but in modern cosmology it is a chasm. The statistical significance of this tension has passed the 5 sigma threshold, a standard in physics which means there is only a 1 in 3 million chance that the disagreement is a fluke. The two measurements are both highly precise, and they are both fundamentally incompatible. The universe of the past and the universe of the present are not in agreement. A quiet crisis has emerged from this numerical gap. The tension suggests that something fundamental is missing from the standard model of cosmology. It is as if we have measured the growth rate of a child based on their infant health records, and then measured the child again as a teenager, only to find they are significantly taller than the laws of biology should allow. The discrepancy implies that between the release of the first light and the current era, an unknown process has altered the tempo of the expansion. The distance is growing faster than our maps predicted. Wendy Friedman, an astronomer who led the Hubble Space Telescope Key project in the 1990s, has spent recent years seeking a third way to settle the tension. She has turned her attention to the tip of the red giant branch, or TRGB stars. These are aging stars that reach a specific, predictable peak in brightness before they begin to shrink. Because they are found in the halos of galaxies where there is less dust to obscure them, they provide an independent check on the Cepheid-based distance ladder. Her results have often sat in the middle of the two camps, adding another layer of nuance to the investigation. The search for a resolution has led theorists to propose several new physics scenarios. One possibility is that dark energy is not a constant, but has changed its strength over the billions of years of cosmic history. This is known as quintessence. If dark energy were stronger in the past, or has become more aggressive recently, It could explain why the local expansion is faster than expected. Another theory suggests the existence of a dark radiation in the early universe, a new type of subatomic particle that exerted extra pressure and accelerated the expansion before the first light was released. Interpretive asides in the scientific record often characterize this tension not as a failure, but as a moment of potential discovery. In the history of physics, contradictions between theory and observation are frequently the precursors to a paradigm shift. Just as the orbit of Uranus once hinted at the existence of Neptune, the Hubble tension may be hinting at a deeper layer of reality that we have yet to name. The discrepancy is a signal that the vacuum has properties that are more complex than a simple cosmological constant. The void is still surprising us. A bridge between the two eras is currently being constructed by the James Webb Space Telescope. With its powerful infrared eyes, the telescope can see through the dust that sometimes complicates Cepheid measurements. It can also detect the faint light of much more distant standard candles. The early data from Webb has begun to confirm the SH Suez measurements, suggesting that the tension is not due to a simple error in the way we see the local stars. The conflict appears to be a real property of the universe itself. The distance between galaxies is therefore a quantity that remains in flux. While we can map the walls and the filaments with increasing clarity, the rate at which those structures are moving apart is a question that defines the limit of our current knowledge. We are looking at a universe that is stretching according to a rhythm we do not fully comprehend. The intervals are widening, and the vacuum is exerting its pressure, but the exact tempo of the descent into the dark remains a subject of quiet, intense scrutiny. As the chronicle reflects on this tension, it becomes clear that the isolation of the galaxies is an inevitable consequence of the expansion, regardless of the exact value of the Hubble constant. Whether the rate is 67 or 73, the outcome is the same. The cosmic web is being pulled apart. The filaments are thinning. The voids are growing. The final chapter of the chronicle moves from the conflict of the measurements to the settled reality of the long-term future. This is the long descent, where the expansion finally wins and the universe settles into its ultimate silent configuration. Chapter 12: The Long Descent. The inevitable consolidation of local matter represents the final act of gravitational dominance within our immediate neighborhood. While the expansion of the vacuum is the primary force on a cosmic scale, the local group remains a pocket of resistance. It is held together by the mutual attraction of its members and the dark matter scaffold that anchors them. Over the next 4 billion years, the gap between the Milky Way and the Andromeda Galaxy will continue to shrink. The two systems are currently approaching each other at a rate of roughly 110 kilometers per second. This movement is a slow, silent convergence that will eventually result in the formation of a single, massive elliptical galaxy. It is often referred in the scientific record as Milkomeda. A merger of this scale is not a kinetic collision in the traditional sense, but a patient interweaving of orbits and gas clouds. Because the distance between individual stars is so vast, it is highly unlikely that any two stars will actually strike one another. Instead, the gravitational fields of the two galaxies will pass through each other, stretching the spiral arms and tossing millions of stars into new, wider trajectories. The gas clouds will compress and trigger a final, brief period of intense star formation. This happens before the new system settles into a stable, rounded shape. The dust will clear, and the two separate families of stars will become one. While this local merger proceeds, the accelerating dark energy will continue to push the rest of the universe away. Every galaxy that is not part of our local cluster will recede beyond the cosmic event horizon. They will be traveling into the unobservable territory where its light can no longer reach us. Within 100 billion years, the night sky as seen from Milkomeda will be fundamentally different. The distant walls and filaments of the cosmic web will have vanished. The great voids will have grown until they encompass everything. The observer of the far future will see only the stars of their own galaxy, surrounded by a total and absolute darkness. There is a quiet finality in the realization that the evidence of the universe's history is being erased by its own expansion. The cosmic microwave background will be stretched to wavelengths so long that they will be undetectable. The distant supernovae that revealed the acceleration will be gone. Future civilizations, if they exist, may conclude that they live in a lonely, static universe, unaware that trillions of galaxies once populated the sky. The isolation that began as a tiny fluctuation in the early universe will have become the defining condition of existence. The era of star formation will eventually draw to a close as the reservoirs of hydrogen gas are exhausted. Across the trillion-year span of the degenerate era, the lights of the universe will begin to fail. The largest, hottest stars will be the first to go, burning through their fuel in a few million years. The smaller, cooler red dwarfs will persist much longer, some for trillions of years, before they too fade into white dwarfs. These remnants will slowly cool, losing their warmth over eons until they become black dwarfs, cold, dark spheres of carbon and oxygen that no longer emit any light. The galaxy will become a graveyard of cinders. A sense of settling occurs when a long, complex process reaches its natural conclusion. In a room where a fire has burned for hours, the air eventually achieves a state of uniform coolness. The embers lose their orange glow, turning first to a dull red and then to a silent gray ash. The crackling of the wood is replaced by the stillness of the environment as the heat dissipates into the walls. There is no sudden end, only a gradual receding of energy until the room is as quiet and still as it was before the fire was lit. The light is not extinguished, it simply dissolves into the background. The transition to this state is a movement toward total equilibrium. As the stars fade, the only active processes left in the universe will be the slow evaporation of black holes through the emission of Hawking radiation. This process, predicted by Stephen Hawking in 1974, suggests that even these massive traps for light will eventually lose their mass to the vacuum. The scale of time required for a supermassive black hole to evaporate is nearly impossible to quantify. This involves numbers with over 90 zeros. The universe will spend the vast majority of its history in this state of slow, cooling decay. The final image of the chronicle is not one of destruction, but of an immense and stable quiet. Entropy, the measure of disorder and the dissipation of energy, will eventually reach its maximum. The universe will become a uniform sea of low energy photons and stray particles, separated by distances that make interaction impossible. The pressure of the vacuum will have pushed all matter so far apart that the concept of an interval will no longer have any meaning. There will be no more distance because there will be nothing left to separate. The void will have achieved its final, perfect form. The journey of the light that began at the moment of recombination will have reached its end. Those photons, stretched by billions of years of expansion, will have become part of the background. Their energy will be so low that they are indistinguishable from the vacuum itself. The lighthouses of the deep past, the supernovae, the quasars, the pulsing cepheids, will have long since vanished. The chronicle of the distance ends not with a revelation, but with the disappearance of the subject itself. The map is empty. The void is still. The stability of the vacuum remains the only constant in this long descent. While the structures of matter were temporary and fragile, the energy of the empty space is persistent. It does not age and it does not fail. It is the foundation that remains after the stars have been cleared away. The universe returns to the state of quiet potential that existed before the first light was released. This is a dark ocean of space that stretches infinitely in every direction, held in a state of perpetual, unmoving equilibrium. The camera pulls back from the cold cinders of Andromeda, moving outward through the thinning mist of the intergalactic medium. It passes the locations where the Great Wall and the Boot Void once stood, finding only a uniform and transparent absence. The scale of the movement increases, receding further and further until the entire history of the galaxies is a small, distant memory in the center of an enormous silence. The perspective continues to shift backward, away from the matter, away from the light, and into the deep, stable stillness of the vacuum. There is a measurable quiet in the absence of motion. The expansion has finished its work, and the intervals have reached their maximum extent. The energy is spread so thin that the temperature of the cosmos is only a fraction of a degree above absolute zero. In this environment, the passage of time is no longer marked by events or changes. The condition is stable. The state is permanent. The universe is a vast, unlit room that has finally achieved its ultimate restful temperature. The stillness is not a void of meaning, but a state of total completion. The story of the distance between galaxies is the story of the universe finding its way back to this silence. The measurements, the tools, and the scientists who use them were all part of a brief, luminous window in an otherwise dark history. That window is now closed. The darkness is not a hostile presence, but a neutral and encompassing reality. It is the baseline. It is the end of the descent. The journey is complete. Rest well.